Welcome to the Explainer. Today, we are diving straight into the microscopic battlegrounds that dictate why some chemicals are rock solid while others dissolve in an absolute flash. We're uncovering the hidden energetic forces governing the very materials that make up our world. Let's get right into it. Think about this for a second. Why does everyday table salt dissolve effortlessly in water, while a piece of chalk simply sits at the bottom of the glass, basically mocking you? It's something we kind of take for granted, right? You sprinkle salt into boiling water, and poof, it vanishes instantly. But drop a piece of calcium carbonate, chalk, into that exact same water, and it does absolutely nothing. Why the dramatic difference? Well, it all comes down to an invisible atomic-level tug-of-war. To crack this mystery, our explainer today is going to walk through 5 key areas. We'll cover lattice energy and ions, the power of ion polarization, thermal stability under fire, enthalpy changes in solution, and finally, the solubility of sulfates. All right, part 1, lattice energy and ions. We have to start at the absolute foundation here, lattice energy. This is the energy arising from the electrostatic force of attraction of oppositely charged ions when a crystalline lattice is formed. Essentially, it's the ultimate glue holding an ionic solid together. When a lattice forms from gaseous ions, a massive amount of energy is released. And the more energy released, meaning a highly exothermic value, the stronger that electrostatic attraction is. But what actually decides if this atomic glue is like cheap sticky tape or, industrial-grade cement? Well, it basically comes down to 2 things, ion size and ion charge. The physical dimensions of the ions completely dictate the strength of the glue. As ionic radius increases, that charge gets spread out over a much larger volume. What does that mean for us? Weaker electrostatic forces, making the lattice energy less exothermic. But on the flip side, as ionic charge increases, say jumping from a 1+ to a 2+ charge, the charge density absolutely skyrockets, and that results in a highly exothermic lattice energy. The ions just attract each other far more strongly. Take the group 1 halides, for example. You can track the lattice energies becoming drastically less exothermic as the negative ion gets bulkier, moving from fluoride all the way down to iodide. For a positive ion like lithium or sodium, as you pair it with increasingly massive anions, the energy drops off. The glue gets weaker because the charge density is simply too low when the radius gets that big. Moving on to part 2, the power of ion polarization. Now, in a textbook, ions are usually drawn as perfectly rigid, happy little spheres, but in reality, things get a bit messy. If you put a tiny, highly charged positive ion next to a large negative ion, a literal tug-of-war begins. The intense positive charge of the cation acts like a magnet, physically distorting and pulling the electron cloud of the larger anion right towards it. It's no longer perfectly spherical, and we call this ability to distort polarizing power. So, what's the perfect recipe for this distortion? An anion is most likely to be polarized if you have small cations, especially when packing a dense 2+ or 3+ charge paired up with a large anion, ideally carrying a 2- or 3- charge. You've basically got a tiny aggressive attacker pulling on a large, squishy, vulnerable target that can't hold on to its own outer electrons. When this happens, the bond isn't purely ionic anymore. It actually gains covalent character. Which brings us to part 3, thermal stability under fire. Let's see how this polarization behaves when things heat up. Take the group 2 carbonates. Magnesium carbonate decomposes at just 540 degrees Celsius. But as we go down the group, the metal ions get larger, their polarizing power drops, and the carbonates become incredibly resistant to heat. By the time you reach barium carbonate, you literally have to blast it to 1360 degrees before it gives in. That is a massive difference for compounds in the exact same family. Let's break down exactly why that happens. Step 1, a small group 2 cation, like magnesium, highly polarizes the large carbonate ion. Step 2, this intense internal pulling physically weakens the carbon-oxygen bond right inside the carbonate. Step 3, because the cation has already done half the work weakening that bond, it takes way less thermal energy to snap it, forming CO2 gas and a metal oxide. It breaks down at just 540 degrees because the internal tug-of-war was already tearing it apart before the heat even arrived. All right, part 4, enthalpy changes in solution. Now that we've seen what fire does, what happens when we drop our tug-of-war into a beaker of water? Well, water molecules are polar. They act like swarms of tiny magnets. The slightly negative oxygen atoms lock onto the positive ions of the crystal, while the slightly positive hydrogens pull on the negative ions. They form ion dipole bonds that violently attempt to rip the separated ions away from the lattice, hydrating them. It's the ultimate showdown, lattice energy fighting to hold the crystal together versus hydration enthalpy, where water molecules are desperately trying to pull the ions apart into solution. Dissolving isn't magic, it's just a brutal thermodynamic calculation between these two forces. Whichever side wins this energetic battle determines the overall enthalpy change of solution. And that leads us perfectly into part 5, the solubility of sulfates. Let's look at the actual numbers for group 2 sulfates, because the drop in solubility here is staggering. Magnesium sulfate dissolves effortlessly, over 1.8 moles per decimeter cubed. But calcium, strontium, and then barium sulfate, the solubility completely crashes. Barium sulfate is basically a brick. Its solubility is down in the 10 to the negative 6th range. How can substances in the exact same group behave so radically differently? Here is the secret to the math. Down the group, both lattice energy and hydration enthalpy decrease, meaning they become less exothermic. However, they don't weaken at the exact same rate. The sulfate ion is absolutely massive. Because it completely dominates the lattice, swapping a smaller magnesium ion for a larger barium ion barely changes the overall structural size, so lattice energy decreases very slowly. But hydration enthalpy, that relies entirely on the changing cation. As the metal ion gets bigger, its ability to attract water drops off a cliff, so the enthalpy of solution becomes increasingly endothermic and solubility severely plummets. If we compare the enthalpy cycles of calcium sulfate and strontium sulfate, you see Hess's law in action. For calcium sulfate, the hydration energy going down is somewhat close to the lattice energy going up. But look at strontium sulfate. The hydration energy drops significantly because that large strontium ion just can't attract water as effectively. The gap at the bottom, the enthalpy of solution, stretches out. It becomes highly endothermic, meaning the crystal demands way more energy to break apart than the water can actually provide, so it refuses to dissolve. So if size and charge dictate this epic battle between crystal strength and water's pull, what invisible chemical tug-of-wars are governing the materials you interact with every single day? The salt on your food, the chalk on a board, the screen you're staring at right now. Their entire existence relies on a hidden math of size, charge, and distortion. It's happening constantly, right under our noses. Thanks for joining me for this explainer, and keep looking for those invisible forces.